get started. In the previous class, we started discussing about formulation of 2D elements for structural mechanics, right? So, we looked at energy minimization as a method to formulate the necessary equations. Energy expression was half stress into strain per unit volume, and that needs to be integrated over the volume of the element. Yeah. So, for one dimensional cases, it is simply half epsilon x into sigma x we saw. For 2D cases, say for example, plane stress, where you have sigma x, sigma y, tau xy, correspondingly epsilon x, epsilon y, gamma xy, the normal strains and the shear strain. Okay. So, you take a product of these things, integrate it over the volume, that is our expression for strain energy. So, in matrix form, it became half of epsilon transpose sigma. Okay. So, that is one expression we have. Integral over the volume of the element, and then the sigma was given as in terms of the strains. So, d into epsilon we put. Okay. Then we put sigma epsilon in form of nodal displacement. So, b into delta E. So, therefore, we got a generic expression for the strain energy irrespective of which is the finite element I am going to formulate, whether it is a triangular element, quadrilateral element with 4 nodes, 8 nodes, whatever. This expression is valid for all the structural mechanics problems. Similarly, the forces, we looked at the distributed forces and concentrated forces acting at a certain point. The point moves through a displacement which is interpolated from the nodal displacements. So, force multiplied by the displacement is the work done, potential of the external forces we got. So, the whole thing we added, we got the total potential for that element, and we took out the central portion and we considered that to be the element stiffness matrix, element force vector. These expressions are valid irrespective of any element. So, I am going to use them to formulate our next finite element in today's class. So, we have the total potential for all the elements, and then the variation perturbations in the total potential expression are obtained by changing the nodal values of displacements u1, v1, u2, v2, u3, v3 all over the structure. So, if this has to be a minimum for equilibrium, then its partial derivative with respect to u1, u2, v1, v2 etc., has to be 0. So, compact notation of matrix algebra, it leads to k into delta is f. Okay. Now, this is your element level equations, which you would assemble and get the structure level for the entire finite element mesh. However many elements you have, you assemble them, you will get the entire set of equations. Is that okay? So, we used it to formulate the element stiffness matrix for a 3-node triangle, but because it is a very simple element involving linear interpolation functions, the strain displacement was a constant b. So, we need not really worry about integration, we directly wrote down the expression. But now, I will go to the next element using essentially the same expressions. I will see how I can formulate the 4-node quadrilateral element and then maybe 8-node element. So, with that you would get a hang of how we are going to do for any element for that matter. Okay. So, let us look at the 4-node element closely, then we would be in for some tedious calculations. So, what we did already for 4-node element is that a generic 4-node element in xy coordinates with the 4 nodes at x1, y1, x2, y2, x3, y3, x4, y4. This is transformed into the natural coordinates element, which is a perfect square, -1 to 1, 4 nodes, and we have the shape functions interpolated using, the node displacements interpolated from the nodal values using the shape or interpolation functions n1, n2, n3, n4. These we derived, we got this type of expressions, okay, in terms of zeta eta coordinates, okay, fine. Now, to get the derivatives in terms of x and y, we used the Jacobian, okay, which relates the derivatives in one coordinate frame to another coordinate frame. It is a 2 by 2 matrix irrespective of the element, because it is 2 coordinates x and y and 2 coordinates zeta eta. So, that transformation is only a 2 by 2 matrix. So, for a 4 node element, we have written down the expression for the Jacobian. It depended on the shape function derivatives and the nodal coordinates, shape of that element. When you have measured the whole geometry, it depends on these two things. So, given an element, that means the nodal coordinates being known, you will be able to compute this. But we notice that because this involves zeta eta terms, it would vary from point to point within an element, okay, note that. So, we did the strains to displacement relation now, epsilon x, epsilon y, gamma xy, let us say. That means dou u by dou x, dou v by dou y, and a combination cross derivatives we will need, okay. So, we will need to transform that, which we attempted to do in terms of the nodal displacements ultimately, that B matrix. So, what I am going to do, you please see, this is a structure you can use for any element for that matter from now. So, what I am going to do is to this third term, dou u by dou y plus dou v by dou x is a pain to handle. So, the way we will deal with it is actually to introduce a set of derivatives as a 4, 1 vector, dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, and then I introduce this matrix B1. So, ultimately the expression that we have is this epsilon is given in terms of B into nodal displacements. So, this will be for this case U1 all the way to V4, this will be 8 by 1. We have 3 strains, so 3, 1. So, I need to get a 3, 8 strain displacement relationship matrix, okay. So, I am going to get it in stages, okay, because I am involving from xy coordinates to zeta eta coordinates, that transformation. So, I will do it in stages. The first stage I have introduced, which is called B1, is a set of zeros and ones, just to streamline the way in which we write it. So, this is one part. The second part is now, you look at this right side, this one that we have, which is dou by dou x, dou by dou y of u and v. So, this I am going to write in terms of dou by dou zeta, dou by dou eta. So, that is the second part, okay. So, you can ignore the bottom half, look at the top half first. So, I am on the left hand side, I am writing dou by dou x, dou by dou y of u and v, and on the right hand side I have dou by dou zeta, dou by dou eta. That matrix will involve Jacobians, because that is the coordination between xy coordinate frame and zeta eta coordinate frame derivatives relationship, that involves Jacobian. The way this Jacobian comes, because it is connecting dou by dou x and dou by dou y of u as well as v. So, please observe how it is written. It is written as a 4 by 4 matrix, but the 2 off diagonal sub matrices 2 by 2 are zeros. It is actually dou by dou x. The relation I have is dou by dou x, dou by dou y of any function is dou by dou zeta, dou by dou eta, correct. So, I have just repeated it twice for u and v in one compact matrix. So, I would call that B2 matrix. Okay. And then finally, the right hand side dou by dou zeta, dou by eta are interpolated through the derivatives of the shape functions from the nodal displacements, because displacement at any point is n into delta. So, the derivatives of that will give me the derivatives that I need. So, this is going to be the B3 matrix. So, B1, B2, B3, please go over it, concentrate for a minute, figure out how they look. So, this is a 3 by 4 matrix of zeros and ones. Okay. Then next matrix is a set of Jacobians, that is 4 by 4, and this is now 4 derivatives in terms of zeta eta being related to the nodal displacement. So, this is a 4 comma 8. So, finally, I will get epsilon in terms of derivatives. Is that okay? How it will look like in terms of the shape functions n1, n2, n3, n4. So, the derivatives, all of them will go into B3 matrix. You will get B is product of B1, B2, B3. Now, if you look at the way in which it is done, B1 does not depend upon the element. It is 4 node element or 8 node element or whatever element, it does not matter. It is just a set of zeros and ones. B2 is Jacobian, 2 by 2 repeated twice. So, that 4 by 4 again, the structure of that does not depend upon the element. The individual elements in that 4 by 4 matrix will depend obviously on the element, because Jacobian will depend upon the shape function derivatives, but the structure is the same. Then B3 is the derivatives of the shape functions. The size of that will stretch. If it is an 8 node element, it will be longer. If it is 4 node element, it is 3 comma 8 or 4 comma 8, sorry. Okay. Totally, I will get the 3 strains epsilon x, epsilon y, gamma x, y in terms of the nodal displacements. That is our B matrix. From this B matrix, I will get the strains and then the stresses, the strain energy, what we have discussed right now. So, finally, the stiffness matrix will be this. Now, comes the problem. So, if you look at this now, the size of this matrix, because it is a 4 node element, each node point can move along x axis and along y axis, 2 degrees of freedom or 2 nodal displacements. So, total over the 4 nodes, it will have 8 unknown variables displacements. 8 displacements, it means you will get 8 equations, or this matrix will be 8 comma 8. 8 comma 8 means you will need to evaluate for any general matrix, you will need to evaluate 64 integrals to get one element stiffness matrix. Okay. I have still not completed, because I have to find the right hand side also. Then only I will get that element equations. Then I probably will have some 100,000 elements. So, for each of these elements, I have to do this calculation and then do the assembly. Okay. So, we notice that this would be quite time consuming and tedious. One saving grace is that this is a symmetric matrix. We have seen in earlier classes the terms in the differential equation and the way in which we have chosen the weight function for Galerkin process or Rayleigh-Ridge process. It will sometimes give you symmetric matrices. In this case, this is giving us symmetric matrices. In structural mechanics, this symmetry you may have come across in solid mechanics courses through some other principle like reciprocity principle. That means, if I apply a load and look at the deflection here, or apply load here and look at the deflection here. So, this reciprocity relationship you must have either read about it or heard about it, Maxwell-Betti reciprocal theorem and so on. So, that symmetry is what is reflected in these matrices again. So, you will need to still evaluate 36 integrals. That 36 comes from 8 by 8 matrix. So, the leading diagonal and then this. This is symmetric. So, this is going to be 36 coefficients. So, these 36 double integrals you will need to evaluate. The other saving grace is that unlike in the xy coordinates, now you are going to do the integration in zeta eta coordinates, which is over the perfect square. -1 to +1. Okay. So, to that extent, the integration domain is kind to us, because we have done the coordinate transformation from xy to zeta eta. But still 36 integrals have to be evaluated, and so we take recourse to computer based integration. What techniques have you probably come across for integration? You would have come across something like trapezoidal rule, Simpson's rule, etc., right? Anyone who has not studied trapezoidal rule or Simpson's rule, in some course or the other you must have come across, right? So, we will just briefly review them, more to just recapitulate what you have already learnt, and then I go for Gauss quadrature formula, which is what we would actually be implementing it in finite elements for our course. So, what did you do in this type of numerical integration? The fundamental idea is simple. When I have to find integral of any f of x, let us say over an interval f of x, x. So, integral of f of x dx over a to b would mean the area under this curve, correct? The area under this curve I need to estimate, and because I do not have a easy looking expression for f of x, like in this case f of x would be actually b transpose db matrix ka a coefficient. So, what I am going to do is, I would think that curve f of x is some known curve. The simplest that you might have come across is it's a straight constant line, straight line. Okay. So, that would be the rectangular rule. So, you would notice that I have just plugged it in as a rectangle everywhere, steps. Okay. Area of the rectangle is a into b, so that is easy to estimate, and I will take the total area to be a summation of all the individual rectangular areas. Instead of 10 rectangles, you may take 1000 rectangles, you will be better off. That is the simplest idea, you must have implemented it. A little better than that, instead of assuming that it is a constant, you would have allowed a linear variation within that small division. You would have allowed it to vary linearly. That led you to trapezium shape. So, it is called the trapezoidal rule. The area under that curve is approximated as the area of the trapezium. That is what you read as trapezoidal rule. If you could do constant and linear, you can obviously do quadratic also, cubic also, whatever curve you want. You get the basic drift. So, next you did a quadratic curve. That is what led you to Simpson's rule. So, quadratic curve approximation, you can see here rectangular rule, trapezoidal rule, Simpson's rule. Basically, the function is approximated using some function, known function, easy function, the area under which you know. So, you keep subdividing and then add them up. Is the concept clear? This is how you learnt, right? Yes or no? Yes, very good. So, I am more interested in how it comes out as an expression ultimately. Okay. What you did, you expressed the area under the curve f of x from a to b. that is integral a to b f of x dx, as being approximately equal to the area of the rectangle or trapezium or the quadratic curve, okay, and then sum it up. But when you summed it up, you would have expressed it in this type of a form, okay, because you can see there it is f1 plus f2 by 2 into delta. Some such formula you would have got for the area of that strip, depending on whether it is a rectangle or a trapezium or a quadratic curve. You will get some area of that, and then you keep on adding it up. But that expression, you eventually give it like this. I am actually going to focus on this expression. I want you to look at this expression as the value of the function. You see what you are got here, the value of the function f of x at x0, x1, x2, x3, x4, like that, wherever, what is the subdivisions you have made, the value of that function, which is multiplied by some weight. In this particular case, the weight is constant delta x or delta x by 2. Delta x by 2 at the two ends, and for all the terms in between, it is delta x itself. That is how this formula looks like, trapezoidal rule. Simpson's rule, if you do, Simpson's rule will also be like this, but what I want you to observe is that integral f of x dx a to b is approximately written as summation that is how I want you to look at the structure of this computer based integration formula. Now, this weight will change. You are evaluating the value of the function at some intervals, approximating the variation to be a constant, which is rectangular rule, linear, which will be trapezoidal rule, a quadratic curve, which would be Simpson's rule. So, but you sample the function at some uniform intervals, multiply it with a suitable weight. You take more intervals, that is, at more points you sample the function, you will be approximating it better and better. Now, Gauss quadrature that we would be using is essentially similar to that, except that so structurally it is the same, W1 into F1, W2, F2, etc., you add it up, okay. Structure wise it is the same, I have written there. But what Gauss asked is that instead of taking uniform intervals over A to B, for example, are there good points inside that AB interval where I should compute, where the accuracy will be better if I am able to do the computation at some xi. So, he asked the question, looking at this approximation approach, he asked the question, which are the points xi where I should sample the function f of x, and what should be the weights, both. In the first case of rectangular rule or trapezoidal rule or Simpson's rule, we did not ask this question, first question. We said it is uniformly split into n divisions, delta x is the size of that division. So, that way we simplified it, but he included xi also into the framework. He asked the question, at which points should I sample the function, and at what should be the weight with which I should multiply it. Both have to be solved. So, I have given the complete derivation of Gauss quadrature formula in my textbook. So, please read that. We wouldn't go through it here, but you would be good idea to read that. I think I built it up from simple logic, so you should be able to follow on your own, but I will give you the result of that question. This is the same Gauss that you encountered in some other contexts also, like for example, Gaussian elimination method. Okay, where else? Gauss. Okay, basically methods to solve Ax is equal to b. Okay, where else? Huh? Where else you come across Gauss? Gaussian distributions. Okay, very good. Where else? Okay, solving Ax is equal to b, one set of algorithms. But even before you came into IIT, you must have read about Gauss. N into n plus 1 by 2 is probably the first time you must have come across Gauss. No? N into n plus 1 by 2. You must have read the story also, that what his teacher attempted to do. Whether it is true or not, I don't know, but very interesting story, that all the children were doing masti in the class. So she wanted to keep them quiet. She probably wanted to do some other work. So she asked them to find the sum of some large number, 1 to 28 or something like that. She thought they will take quite some time. You have to write down 1, 2, 3, 4, 5 up to 28 and add them up, right? So there was this one boy in the class who said, he wasn't doing anything. So she thought that this guy is up to mischief. So she pulled him up and asked him. She said, I have already done it. How did you do it? He showed the answer, and that's correct answer. So how did he do it? Right? He wrote 1 to 28 and then 28 to 1, one below the other, and then summed it up. So that is what you have as n into n plus 1 by 2 as the formula for the sum of n in numbers. Okay. So the same Gauss, you would have come across him in physics also, electricity, electrostatic potentials, fields and all that, right? Okay. So a lot of places you would have actually heard about him. So the same Gauss, so his contribution about the quadrature schemes. Quadrature is essentially integration, finding the area under a curve. Okay. So that is what we would be using here. So he asked this interesting question, ki, what should be my sampling points xi and what should be the weights along with. So his approach was that, why was he asking this question? So he wanted to know, supposing I use 3 points, how can I maximize the curve f of x up to which my formula will be accurate? If I am using 4 points, how do I maximize that I can approximate any f of x up to this curve? So that is what is Gauss' basic idea. So we would find, I think it's probably there in my next slide. Yeah. So he found the answer that if he took n points the way he has developed it, you can approximate any f of x which is a polynomial up to 2n minus 1 degree, and the formula will be exact. So based on that kind of questioning, he came up with this formula. What is this formula? I will only discuss here what is the result and how to use it in our calculations. How he came up with something like this, that derivation is there in the book. So you please refer to the book and read it there. It would be interesting to just, for the fun, how he thought through this type of a question. Okay. So what does he want you to do? He says, if you are using 1 point only, in the interval -1 to 1, in the interval -1 to 1, so suppose zeta, this is 0, -1 to 1. and in this interval some function is there. Okay. So, there is some function, you are approximating it with only one point. Where should that one point be? Is a question that he asked. So, that answer turns out to be that that point should be, as per this table, 0, the center point of that interval. Okay, fine. So, this is the point. Okay. Now, he is asking you to multiply it with a weight factor of 2. So, the approximation that he is giving you, integral -1 to 1 f of x dx, sorry, f of zeta d zeta if you want, because x can be from a to b, whereas zeta and eta are from -1 to 1. F of zeta d zeta is approximately equal to, for a 1 point rule, so weight is 2 and f of 0. So, what is f of 0? Say, let us say this is f of 0, okay, and weight is 2. What does it mean? Weight is 2. What is 2? What is 2? Yeah, interval. The interval is 2, right? So, what he is essentially asking you to do is what? When you multiply it by 2, you will get the area, means what? What is the shape you are approximating the function to be? That is all. So, he is said, if it is only one point, then simply take it as 0, the center of the interval, whatever is the value, assume that it is constant throughout that interval. So, that is the area that you will approximate. So, now with that logic, now if you are using 2 points, then he says you use 1 by root 3 and minus 1 by root 3. Okay. 1 by root 3 is how much? 1 by root 3? 0.7, something like that, right? So, here, so minus 1 over root 3, 1 over root 3. If it is usual rectangular rule or trapezoidal rule or so, 2 means you would have taken it to be 2 equal divisions. That is not what he is doing. He found out the answer to be 1 by root 3 minus 1 by root 3. At that point, what is the value of f? You sample the function f of zeta at that point and multiply with what weight? 1. So, what he is asking you to do? Essentially, what is he asking you to do? 2 rectangles, correct? 2 rectangles. So, whatever is the value here, whatever is the value here, 2 rectangles, because that is 1 is this interval, 1 is this interval, value of the function multiplied by this 1 unity, value of this function here multiplied by this interval. So, that sum is your best approximation to the area under the curve. If it is 3 points, now again he has some 3 selected points he gives you and then corresponding weight. Okay. Is that fine? So, is the method understood? How he got this? You go back to your rooms and read from the book. Okay. In the textbook I have derived all that. Now, let us try it out. You try this example and see how you get that. So, let us see integral minus 1 to 1, 1 plus, sorry, 2 plus zeta plus zeta squared d zeta, suppose. Okay. So, this is your f of zeta. Okay. So, if it is 1 point rule, one-point Gauss quadrature, this is approximately equal to, at zeta is equal to 0, correct? If it is 2-point Gauss quadrature, then zeta is 1 by root 3 minus 1 by root 3, W is 1, W is 1. So, this is approximately equal to weight 1 into 2 plus root 3 plus, no sorry, 1 by root 3, right? Squared plus again 1 into 2 plus minus 1 over root 3 plus minus 1 over root 3 squared. So, check and tell me how much this is. 14 by 3 means how much? 4 point. 14 by 3 wouldn't help me to see if it is converging. 4.6 what? 666. Okay. Okay. Fine. So, you are now slightly better. From 4, you have become 4.66. Now, complete it for 3 points, for example. You can do it for 3 points. I will give you the table. Do it for 3 points. I is root 6, 0 and minus root of 0.6, sorry. Root of 0.6 and 0 minus root of 0.6. Weights are 5 by 9, 8 by 9, 5 by 9. How much you got? 4.667. Right? You would get the same. Why? Because he has also told you that any polynomial less than or equal to 2n minus 1. So, if you have taken 2-point rule, so 2 2's 4 minus 1 cubic, okay. Up to cubic polynomial you will be able to integrate exactly. So, you have already got the exact result. With 3-point rule you can 2 into 3 6 minus 1 5, 5th degree polynomial you can integrate up to that exactly. So, you have already got the exact result here, okay. Now, when you do the next problem, then you would notice, because the next problem I have chosen is cos expression. So, okay. So, okay. Please check and tell me what you get. 1-point rule should be fairly straightforward. Yes. 1-point rule is zeta equal to 0. So, cos of 0 is 1 and then multiplied with a weight function 2. So, this is 2.0. Okay. So, 2-point rule, 2-point rule weights are this and the sampling point is this 1 by root 3 minus 1 by root 3. 1.998, 899 again. Is that correct? 1.6. 0.997. Okay. Okay. Any other answer other than this? Try out with 3 point. Same answer. 1.997. Is what is the exact value of this? Then is this one. Cos expression minus 1 to 1. What is the exact value? Integral cos exact expression is 1.27. Who's still having a doubt whether it should be degrees or radians? You tell me whether I should take degrees or radians. ये भी doubt हो सकता है. So what is the answer? 1.2323. ये सही है. Okay. 2-point thing. 1.232. Then 1.27. So you would see that as you increase the number of points, you are approximating it better and better. But cosine function, being cosine trigonometric function, it would not be exactly a polynomial. So you wouldn't get exactly the integral value, but you are approximating it better and better. So now coming to, this is the general method. He has developed it without any intention of application to finite element method, right? So we are adapting it to finite element method. In finite element method, our integral is this fellow. Okay. So I have to extend it now to 2 dimensions, because in the one dimensional case, I really didn't bring this aspect in. Even when we chose quadratic expressions, the integral was easy to manage. So I actually integrated it out exactly. Okay. So now to extend it to 2 dimensions, we do it this way. So I do along zeta and eta, I take it as a product. The function is evaluated. When I say 2-point rule, for example, it would be 2 points along zeta and 2 points along eta, and the locations of the points are the same, 1 by root 3 and minus 1 by root 3. So you evaluate it at those 4 points. So these are called Gauss quadrature points. Okay. You evaluate the function at those 4 points. What is the function to be evaluated? For us, this is the function to be evaluated. The whole integrand that varies from point to point in general is B transpose dB into thickness, also could vary in some cases, into Jacobian. Why all of these are varying? Because we have written B1 does not vary, but B2 has Jacobian that can vary from point to point within the element, because zeta eta vary from point to point. Then B3 has derivatives of shape functions, those can vary from point to point. So, the B matrix will vary from point to point. Even if you assume linear elastic isotropic homogeneous material, D does not vary, but again B will vary, B transpose D, B, thickness and then determinant of Jacobian. So, that whole expression matrix I have to compute at each of these 4 points and then add it up. If it is a 2-point rule, therefore, I will compute this integrand at 4 values. At the 4 points zeta eta values, I am going to compute this 8 by 8 matrix and multiply it with the suitable weights Wi, Wj and then add it up. The way we have done exactly this, same way we will do it in 2 dimension and the integrand is this B transpose Tb. So, obviously, this 8 by 8 matrix 4 times calculation, all this will be done inside the computer program, not that you will do it by hand. So, this is how it will look like. It is not necessary that you have the same number of points along zeta and eta. You can, if you think in your shape functions, zeta has higher degree terms compared to eta, then you can change that also in the integration rule. So, I have just illustrated here 2, 3 rule. So, 2 points along zeta, but 3 points along eta. It is up to you how you do it. The weights will be different, the sampling points will be different. You get the basic idea of how Gauss quadrature method works. So, we have now eliminated this or simplified this 2-dimensional integration, double integral evaluation over the domain of the parent element -1 to 1, -1 to 1 by just simple function evaluations at selected points. The selected points are Gauss quadrature points and the weights are Gauss quadrature weights. So, you multiply these two and keep adding, then you will get the entire stiffness matrix. Okay. So, this is how all the evaluations in zeta eta coordinates are done for the integrals. In your ANSYS, Abacus, COMSOL, whatever software you use, they would use this. It is not necessary that you should use only Gauss quadrature rule. What is necessary is to be able to compute that integral inside the computer program. I have illustrated it using Gauss quadrature rule. If you do not like Gauss quadrature rule, you can use trapezoidal rule also, Simpson's rule also, does not matter. Okay. But some rule like that you have to use. You would also see in the literature other quadrature schemes being implemented. Okay. Yeah.
In this case, it will be frequent along the entire and go along only near bias towards it.
But your shape function must have been like that. See, how will I choose 2 or 3 points? Why will I choose? Because it is dependent on this. If I take 3 points, 2 into 3, 6 minus 1 up to 5th degree polynomial, I can evaluate the integral exactly. So, if my element formulation tells me that it is likely to have higher degree polynomial terms in terms of eta, I will take more points there. So, you have to see which element you are formulating, what are the shape functions, what has gone into the Jacobian, B expressions and so on and so forth, then you take a call. Okay. Now that we are in this point, let me put some extra twist to this to just make you think. Those of you who are interested can read up about it, we will not discuss it in the class. Now, do we want to evaluate it exactly? Comes the question, right? So, it is natural to think that I would like to evaluate it exactly. Integral f of x dx, you would like to find an exact value. But sometimes you may ask the question, why do I need it exactly? Why I am coming up with this question? Now, I think in the one of the very classes before the mid semester, when we solved problems, we asked the question, if I am looking for displacements, stresses I use 100 elements, I get some answer. I use 1000 elements, I get another answer. I use 10,000 elements, I get another answer. I use 100,000 elements, I get a different answer. So, I am thinking that I would keep converging towards the correct answer. That is the whole premise of our technique. Now, you ask the question, do I converge from below or from above? That question also we asked and addressed that. You remember or you do not remember? So, there is an exact value that you are trying to approximate. Okay. As I increase the number of finite elements, am I going to approach it from below or from above? Okay. Was one question we raised. Supposing, okay, I know that I am going to approach it from below. Okay. K into delta is F, right? For our, sorry, this F and this F do not get confused, or I would say P maybe, force, load. Okay. Stiffness into deflections is equal to load. Okay. If I am going to approach it from below, that means I am overestimating the stiffness, because for a given load, what is the deflection I am trying to find? I am approaching it from below, that means my K estimate is on the higher side. Knowing that I am estimating it on the higher side, can I intentionally try to deflate it a little, because I know that K is on the higher side, that is why I am approaching it like this from below. So, I would intentionally evaluate this fellow wrongly, so that for the same number of elements, my solution may be lifted up a little. It will be better than exactly calculating K. So, people intentionally do what is called reduced integration. Now, once you have started this question, usually it does not stop there, right? Now, there are various terms in the stiffness like this, and in more complex problems, even more terms may be there in the stiffness. Like for example, now imagine that this is the blade of a turbine or high speed rotor. Okay. So, this fellow is rotating at a very high speed, correct. So, there is a force that is acting on every mass point as this rotates at omega, that tends to pull it away from the axis of rotation. Now, there are gas pressures acting on the turbine blade, which are transfers to the blade. The blade tends to deflect because of this load, but because of this force that is tending to pull it away, the blade is actually stiffer than without the force. If there is no force, you can try out this experiment after the class with your friends. Just pull out your hand, somebody applies a force, then the hand will deflect. But ask another friend to pull this hand, then this will be a little stiffer because there is a tensile force. Contrary, if you push it, compressive force, then this will become less stiff. So, more deflection will be there. So, there will be a force interaction between the in-plane force, stiffening force, and the out-of-plane load. Okay. So this structure tends to become stiffer. So there will be additional terms other than these in such problems, because the governing differential equation which we solved for say a beam had only up and down displacement. It had nothing to do with, we proposed the simple Euler-Bernoulli based beam bending element, right. So we didn't consider anything more complicated than that. So there will be additional terms because of this now axial coupled with bending. So now when you talk in terms of reduced integration could potentially lead to better results with the same number of elements, rather than I don't have to do 100,000 elements, maybe I can get it with 1000 elements. Then the question people asked is that, is it necessary to apply the same integration rule for all the terms in the equation? Can I use for some rule for some terms, some rule for some other terms? Can I then improve the accuracy of the solution? So then somebody came up with the idea of what is called selectively reduced integration. I have given you the basic concept of integration rule, Gauss quadrature, and the Gauss quadrature rule idea. Then we looked at this convergence behavior and brought in this. Now you can read it up about this reduced integration, selective reduced integration. These are typically implemented inside the software that you are already using for your course projects. You can go back, now that you understand, you can use the software more intelligently. You can try to read up how is the, supposing you are using quad 4 element, how is the formulation being done in your software for this? What is the integration rule that is being implemented? Is it the same integration rule for all the terms in that stiffness matrix, or they have tried to meddle with it, reduced or selective reduced integration and so on? For which elements he has done that and why? All these questions you can now start exploring in your software, so that you become more advanced level users of that software. Okay. But we wouldn't go into those details, but I have just highlighted it for your own inquiry after the class. Okay. So now I will upgrade ourselves to the quadratic variation of the same element, like we did for the one-dimensional problems. I proposed the 2-node element, and then I brought in the third node, made it quadratic shape functions. So in the same way, from quad 4, I will go to quad 8 element. Formulation goes almost on the same lines. We have already discussed this idea of whether I should use subparametric or isoparametric or superparametric. What we discussed at that time was that there are two things that I am doing interpolation for. One is the coordinate transformation, another is the field variable variation. If both are done using the same set of shape functions, then it will be called isoparametric. So we recognized that there could be subparametric and superparametric elements, but we limited our focus attention to isoparametric elements. So I will go further with only isoparametric formulation. So for isoparametric formulation, now you have 8 nodes. The element is still the same square -1 to 1. So 1, 2, 3, 4, 5, 6, 7, 8. Sometimes you will see that another node is put here at the center, that would be the 9th node. Sometimes you will see that it is not there. We might discuss it a little later if necessary, but right now let us not get distracted. With one element type, let us see how the formulation goes. That is how we are looking at it right now. So if you look at this now, this is the zeta eta coordinates. In the real physical coordinates, it could be curved element. in the xy coordinates. So, the shape functions etc. are given indicated there in terms of n1, n2, n3. The size of the matrices is something that you need to pay attention to, because it has 8 nodes. I am going to write u1, v1, u2, v2 etc. for all the 8 nodes. So, it will be 16 displacements for that element, and so it is matrix is 2 comma 16 and then multiplying 16 comma 1, because at any point within the element ultimately you can have along x axis u displacement, along y axis v displacement. These are interpolated from the nodal values using the shape functions for an interior point. Because there are 8 nodes around, there are 16 nodal displacements, and these two u and v are interpolated from this 16 using the shape functions. Okay. Once you have done that, then you differentiate it, you would get same b1, b2, b3. b1 does not change, 3 comma 4 remains a set of zeros and ones, it is not changing whatever we got earlier. b2 is, let me see, it is here or it was here. Yeah, b1 was this zeros and ones, that does not change from one element to another element. b2 is the set of Jacobians repeated twice. So, it is a 4 by 4 matrix. Because I am dealing with xy and zeta eta, so only 2 by 2 Jacobian, this also does not change except the structure, but the inside elements will change because now the shape functions are different. So, their derivatives will be different. And B3 is size will be changing now because there are n1 to n8 rather than n1 to n4 only. So, this becomes even a bigger, longer matrix. So, it would be 3 comma 16 ultimately. Jacobian remains the same structurally. Inside that 2 by 2 set of elements, coefficients will be summation from 1 to 8. What are the shape functions, 8 shape functions? I think we have discussed it in one of the previous classes. So, you can take the equation of some lines, product of those things and then derive it, you will get it like this. They are quadratic in zeta and eta. So, now when I try to do the evaluation of the element stiffness matrix as B transpose DB, B being B1, B2, B3, B2 is the derivative Jacobians and B3 is the derivatives of the shape functions. So, it is ultimately going to be a 16 by 16 matrix, because there are 8 nodes, 8 into 2, 16 displacements. So, it is going to be a 16 by 16 matrix. That means, in general 256 coefficients need to be evaluated. For one element, you may have a large number of elements. So, when you are doing course project, when you are asking software like ANSYS, Abacus, COMSOL, whatever software you are using, okay, you will mesh it with the most refined mesh that is possible irrespective of whatever is the problem you are solving. So, please have some sympathy for the computational effort involved. If you are choosing 100,000 elements with quad 8 each element, so for each element it will be 16 by 16, that means 256 coefficients to be evaluated, that for 100,000 times. Then assemble all of them, then you will get the entire matrix Ax is equal to B. Is that making sense? So, when you press the laptop asking it solve, okay, this is what it does. If you were to solve it, then FEM would not have been this popular. No design office anywhere in the world would have ever touched FEM, because it is being, all this is being done in software. We are comfortably using it without actually bothering how much is the computational effort and so on. But as the finite element formulation experts, all of you, you must understand what is the computational effort that is going behind the screen. That is why we get into all these details, so that you understand now, you become more intelligent users of software. So you choose now the number of Gauss points needed based on the shape functions depending on the element. For quad 4, 1 point integration may be enough. For quad 8 or 9 quadratic shape functions, you may need 2, because 2 into 2, 4 minus 1. So up to cubic you can manage. Okay. For cubic shape function elements, you may do 2 or 3. Okay. Like that, you have to decide depending upon the nature of the shape functions or the functions in the derivatives of the shape functions, because that is what is B, but it is B transpose into D into B. So it is like square of that derivative. So what is the ultimate expression that is going to be f of zeta eta? What is the order of the terms in that? Based on that, you have to decide this. So I will just illustrate for the triangular elements also. Gauss quadrature rules are developed. It's a little more involved or a different style of doing it, because here now we proposed L1, L2, L3 as the 3 coordinates in triangular elements, but obviously being a 2-dimensional coordinate frame, 3 cannot be independent, one of them has to be dependent on the others. So L1 plus L2 plus L3 is 1, we said. So the way in which the numerical integration would be posed is as shown there, minus 1 to 1 minus L1, it should be 0 actually, sorry, 0 to 1 minus L1 and then 0 to 1 in terms of DL1, DL2, because it is, if you think of any strip that you have done, you would do this kind of integration, right, from here to here, and then swipe this strip across. So imagine that on the triangular element, it will turn out to be 0 to 1 minus L1, that will take you to that other line, and then sweep it 0 to 1. So that is how it is implemented in the computer program for triangular elements using the quadrature formula as this. You had done one single point rule for zeta eta coordinates was at 0. For the triangle, it is 1/3, 1/3, 1/3. That is the centroid of the triangle. When you are evaluating using 1 point rule, then you evaluate the function at the centroid, multiply by the weight as 1. So it is constant throughout the triangular domain. That is the value of the integral you will get. Like that, it has been developed. So these are implemented for triangular elements. Once you understand the concept, then you can figure out that how the numerical integration is done. Okay. Okay. So this helps you to evaluate the equations for a single element. Now you have to assemble for all of them, then ultimately you will get this type of equation, k into delta is f. Now what would be the size of n? What is the n that you have got so far in your course projects? What is the biggest mesh that you have used? I keep taking reference to this course project so that you get reminded of your commitment to do this course project 30% weightage, and you are making sufficient progress in that, because by the end of this month you need to submit it, okay, for final evaluations. So coming back to the question, what is the largest size that you have chosen so far? How many degrees of freedom, so to say, how many variables? Whatever be your problem, what is the biggest size? 100, 1000, 10,000, or you have not yet got started with your course project? Okay, so it's time for you to buckle up, okay, solve a problem. So I wanted you to appreciate what would be the computational effort involved. Can we estimate? How do you typically think of computational effort? How is it quantified? Supposing in an equation Ax is equal to b or k delta is equal to f, n comma n. How is computational effort talked about in terms of what? Memory, okay. One is memory storage. So, n comma n coefficients you need to store for the left hand side, fine, and each element will be stored in a real number format, right. So, how many bytes it needs multiplied by n comma n, that is your amount of storage, okay, fine. Then you have to solve it, right. How do you, time required to solve will depend upon n comma n. So, you would estimate it in terms of the number of floating point operations, multiplications, divisions, additions, subtractions, what all you are doing in that using any algorithm that you have, Cramer's, Gauss elimination, Gauss Seidel, whatever. So, we will try to spend some time on that to make you appreciate what is the kind of computational effort that is involved in solving these equations. Then you would know, but I think you are planning to come up with a problem for next class that they have to solve by hand. So, next class we will make you solve a problem by hand, so that you get some idea of how actually the whole series of computations is going on. We will choose a very simple problem, so that you can actually do it by longhand, but that is a kind of a one-off case. Most of the computations will be done in the program. Okay. So, I think we will stop here and continue in the next class.